Welcome to the virtual laboratory session on metal forming processes. We have discussed metal forming theory, the problem statements and everything in the previous lectures. Now the laboratory session, how does metal forming happen, what is general simulation. In the metal forming simulation that is there in virtual format available developed by the VLabs is a little different from what we did before. Here generally the CFD simulation, computational fluid dynamics simulation is there, in which metal forming is being shown for different parameters you select. For example, you select hot forging, you select specific temperature, you select specific rate of the ram movement or so. You will see the forces and temperature change, and that will be differently shown in different colors that I will demonstrate you here. And a complete laboratory is available for metal forming developed by virtual laboratory. First I will come here at Google, I will say virtual lab metal forming. The first link that you get here is metal forming virtual simulation lab. I click here, it is opening. So this is the interface of the virtual laboratory, if you see. So I am just zooming this out for you to appreciate and so that the visibility is better. So we have home, where motivation, metal forming applications in this you can see different kinds of applications of metal forming are given, and all these theories given in home. In the equipment, different processes, upsetting processes and extrusion processes are given. In upsetting processes, different upsetting processes, for example, gravity drop hammer description, gravity drop hammer kinematics, knuckle joint press, and so all these are given. Let me just go through one. This will show you the video on the upsetting equipment, that is a gravity drop hammer. So this video is always connected to YouTube here in this virtual lab simulation that is developed. You can watch this video on YouTube as well. And also there is a narration when you are watching a video. Though I am teaching this, I am demonstrating this laboratory, I will tell you what is happening. If you play this video on YouTube, then there itself the developers have given their own narration that what is happening, what is the hammer, what are the components, and different simulation. When you see, you will also see the narration there as well. So here you can see this YouTube video has come. If I play this video, it will show that the gravity drop hammer is working like that, and there is only because of the weight only it is dropping down, and different components are given in the left hand, that board, ram, dies, anvil, forging stock, and on the right hand side it is played. It is only 1 minute 25 seconds video. But this is a video on gravity drop hammer. I will walk you through the processes such as upsetting, extrusion, multi-step forging, rolling, sheet metal. A big range of the processes are here, but I will only go through a specific few processes which are more commonly used. Let me first come to the upsetting process. In this you can see the theory about upsetting process. What is upsetting process? It is a free forming process by which billet or portion of workpiece is reduced in height. Usually plain parallel plate is here, and ASM handbook 1988 is quoted, from which this definition is taken. The components, the equipment setup, the video about generic equipment setup, it is all given here. About upsetting, the generic formula of the upset strain and upset ratio, that is also given. This is the theory about the upsetting process and how do the metal flow happens, because there is a bulging here of the metal that you can see in the video. When the upper die and the lower die is there, upper die is moving, lower die is fixed, and this bulging is happening. How are the forcings flowing? And you can also see the mesh. There is a triangular mesh. What is the expansion in the mesh, and at what point these specific nodes are moving? So this is upsetting process. This is the billet, this is bulging, and this is the product that has been gotten. And based upon the die velocity, the metal flow rate changes, the property of the products also changes. Now in upsetting, if I come to simulations, so this is one simulation that is given about the forces, how do those travel. For example, if I play this video in which material is aluminium, zinc 5.6, magnesium 2.5, copper 1.5, height is 100 millimeter, diameter is 100 millimeter, and billet temperature is 300 degrees centigrade, die temperature is 250 degrees centigrade, reduction in height is 50%, and press is hydraulic. If I play this video, so this is an upsetting process in which lower die is fixed, upper die is moving. So it is open die forging process as is studied as well. So it is extensively used for shaping, etc. This is all narrated there in the video, you can watch that. And when the load is applied, you can see the color change, and there in the left hand side you can, this key of the color is also given. So the expansion of the nodes, you can see how the strain is happening. The color is moved to orange, it has moved to red color now. So it is reset, and this is axisymmetric process in which only one part is simulated. So only to understand this video is given. There is another video, if I play that. So this process is regarding the force during the upsetting operation. You can see the metal forming simulation is there, and this here you can see the graph that is there, that is showing the force. So matic is plastically deformed here. So it is open die forging, as I said. You can see this is happening. Once the force is being applied, you can see the change in the force that is happening, the forging force evolution during upsetting process. How is the force varying here? You can see this graph. The force is increasing. The red line is representing the force. Yeah, it has come to maximum. So this was upsetting process simulation. Let me just come to the simulation bench. Simulation bench means it is showing what different parameters we can fix for this specific operation. For example, in the upsetting operation itself, you try to pick aluminum material with L by D ratio as 1.0 only, and coefficient of friction as medium. The velocity of upper die, that is the speed of the die that is moving, is 10 millimeter per second, and we would like to see the simulation for hot process. Let me submit this. There is a video, and there is also the subtitles of the videos are given below itself. The video shows the upsetting operation taking place during hydraulic press. The initial billet of aluminum L by D ratio 1 is taken hot, and upsetting medium friction for billet and dies is shown on the top of the end of the video. For this medium upsetting forging process, you can see this here. If I even turn this to the full screen mode, you can see here in the top, upsetting process, hot forming friction, medium L by D ratio 1, die velocity to 10 millimeter per second. Whatever we selected is presented there. I exit the full screen mode, and I will just play it from the middle itself. You can see how the forces are going. So this is the force in tons and how it is varying. So this is represented here. There is a 50% deformation that is represented in this simulation. This is the simulation way this hot metal forming is presented here, because it is better to understand the forces which are going. And on the left hand side, you can see this color is representing the equivalent strain, how the strain is happening. So this was the simulation bench for the hydraulic press. Now comparative simulations are also there. Effect of different materials, effect of friction, effect of temperature, effect of ram velocity. For example, if I try to see effect of different materials, you can see the simulation is showing the simulation of different materials. So this is written in the video, name is case 1. So the top left quadrant here is copper, and top right is aluminium, and we have titanium and steel on the bottom left and the right respectively. You can see how the forces are varying in different kinds of the materials. This kind of the comparison is also given here. So titanium, as you know, is very hard material, so the forces would be very high here. The simulation is also given. Then we have the applications here for alloy wheel, brass forged part, forged piston, mud guard, pattern making are there. There is a self-check quiz as well here, as it was available in almost all the simulations that we studied. Here in this quiz, the questions are there. So self-check quiz for upsetting process First question is the virtual simulation lab website shows information about which manufacturing process. Obviously, it is showing for metal forming. The contribution of Indian forging industries in global forging market in percentage is, it is given 5% here. The main purpose of upsetting operation on billet is to, the main purpose is to increase the diameter and decreasing height. The number of presses shown in upsetting process module are 4 presses were shown. This is question 4. Question 5 is L by D ratio used in interactive bench of simulation. There were 3 L by D ratio of options available, 1.0, 1.5 and 2.0. Velocity of upper die in a simulation for upsetting operation is, this is just to make sure that whatever we have done that, and we could just recall the things. It was 1 millimeter per second and 10 millimeter per second. A material which is not used in simulation of upsetting operation is, here titanium is used, aluminum is used, copper is used, lead is not used here. In upsetting operation, which die moves? Upper die moves. Which process involves increasing the cross section area by pressing or hammering in a direction parallel to the original ingot axis? What is this process? It is upsetting process. Upsetting process is an open die forging process. Let me submit. Once I submit, they give me, okay, this is your answer. The column 2, the column 3 is the correct answer. Total we have scored 10 out of 10 points, and this is the simulation on the upsetting process. Similarly, I will keep going through simulations of different processes. For that, first we have to come again to the home button. Home button, I will click here, or home tab, I will click, it will come to home. So I will again select another process. For example, I will select extrusion now in processes. A generic simulation about extrusion is given here. So what is the hot extrusion process? So you can see a hot extrusion process is given here. So it is a metal forming process where heated billet is forced to reduce its cross section by friction. So first video is the hot extrusion of pipe. You can see in between we have a mandrel that allows only pipe material to come out, and right hand side video is about the complete rod that is not hollow from inside. So these are the two simulations, and different forces are also given here. You can go through the processes here. Simulation part I will come to. So this is generic, how does the extruded bar come? So this is a billet, it is reduced in diameter and the length will increase. So metal flow in steady state extrusion process, that is given. So forward extrusion, then extrusion load, peak load, friction load, everything is given here. Then we have the optimum process conditions. Maximum extrusion load is increasing, maximum extrusion exit temperature is decreasing. In between at the intersection point, there is an optimum process conditions. So this is regarding extrusion. Let me come to the simulation of extrusion. Comparative simulation. It will compare solid and pipe extrusion. So if I click here, it has given a video where on the left hand side you will see the solid extrusion, on the right hand side there is a pipe extrusion. So the die angle is specified here, 60 degrees is given here, the speed is 1 millimeter per second. Extrusion process for aluminum is given in both of the halves here. The graph between extrusion force and pilot height shows the extrusion forces are high during pipe extrusion than the solid shaft extrusion. So here temperature variation in the billet is being shown here. Temperature variation, you can see the color. The red region shows the maximum temperature. It is also given here. The red region shows the maximum temperature generated at various cross section. 1/4 of the solid shaft is being shown over screen so that the inside view is clear because the shaft is axis symmetric. So this is extrusion. So let me come to do a comparative simulation of the effect of temperature on the extrusion or in the extrusion process. So this is a video that is showing the 3 parts. The top part is the pipe extrusion, the left half bottom is also pipe, the right half bottom is the rod extrusion. So on the upper half, the ram velocity is 1 millimeter per second, it is given here. Friction is 0, die angle is 60 degrees, and it is specified there is no friction in the cold extrusion. And the lower left part is the ram velocity with 1 millimeter per second. The die angle is 90 degree, and there is no friction, that is also assumed here. In the right hand side, it is 45 degrees of die angle, and high friction during this hot extrusion process is given. So there is a comparison between the 2 cold extrusion and 1 hot forming process. So this is cold, the top, the left bottom is cold, the right half is hot. So the comparative change or flow and speed that you can see here. So as the pilot height reduces, the force required to the extrusion of pipe increases. So this is the temperature, this color shift shows the temperature. So this is the extrusion process. So there are certain applications, for example, in seamless pipe, in pipe extrusion, in turbine blade, in golf stick, and there are certain special cases, certain cases of extrusion for different variations in the speed, in the type of the extrusion that you pick, hot and cold, the types of material, those are given here that you can walk through. And self-check quiz I will now come to. So which country has maximum contribution in worldwide forging industry? Europe. The type of extrusion processes involved in metal forming are, there are certain types of extrusion processes, and 4 types are given in this theory presentation that is given in this virtual simulation setup. Parameters which separate cold forming process from the hot forming process is the recrystallization temperature. Below the recrystallization temperature it is cold, above it, it is the hot forming. How many types of presses are shown in extrusion process module? I have walked through 10 different kind of presses here. The force acting on workpiece during extrusion operation is, what is the force acting? Obviously it is a compressive force. I am zooming it out. The simulation bench of extrusion process for aluminium, the velocity of ram used is, this is just to recall whether we have used the right conditions or not. It is 1 millimeter per second and 5 millimeter per second. The diangles used in the simulation of extrusion process for aluminium are, I can't recall, let me pick, it was 60 degrees, maybe answer A, 45 degrees, 60 degree, 90 degree. I will pick 10 degree, 45. Let me pick a wrong answer as well, then we will see what happens. Metal extrusion process is generally used for producing uniform solid section, uniform hollow section. It helps to produce both. For successive extrusion, the metal should be ductile, malleable, plastic, tough. It should be plastic. The extrusion chamber, die and ram are generally lubricated by vegetable oil. So these are all questions. I will not walk through all of them. So there are 18 questions. If I suppose mark some of the questions and some questions I even miss, what will happen? I will submit the result. Only the questions that I have marked 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12 and 13, for only those the answers would come. That means to understand that the right answer, you should mark the answer. You cannot leave it. If you leave it, the right answer would not be shown. This is designed in this way. So it has given 9 score, that is 9 answers are correct. So the answer that is not correct, that is just marked randomly. This is 45, 60, 90 degrees, the correct answer for the diangles which are shown in the simulation, and 211.2 millimeters and 157.5 millimeters were the correct answer for the questions 12 and 13. So this was the extrusion. Again I will come to home and I will come to another process. I will pick multi-step forging process. Multi-step forging, that is, first step is to increase the dia to make a cup or so. Second step might be bending from the top. The first step could be maybe transforming the shape from a circular to a hexagonal shape. The second step could be making holes over it. So this is multi-step forging. So let me just go through the multi-step forging. So there are certain steps in multi-step forging which are given. For example, I will just pick equivalent strain forging force. If I pick this, you can see how is equivalent strain being shown here in this forging. This is a raw material here, and you can say a triangular mesh here. So to develop the CFD module here, this mesh is generated or created. So I'll play the video and you can see the die moving, and the video shows upset stage, that is in step 1, where it is upset, followed by a blocker stage, that is step 2. This is second stage in this blocker, will give it the final shape. So this setup is given on the left hand side, right hand side shows the forces which are happening. So blocker die, you can say in step 2 is bringing it to the shape that is required finally. So this is a graph between upper die versus pilot height in 2 successive stages. This is what it is shown here. So these are the steps in the multi-step forging. Step 1. Step 1 is upset stage, and step 2 is the blocker die final shape getting stage. Now in multi-step forging, certain other steps we can see. Front and the top view could also be viewed, that how does it look like from the front and from the top, or how does it vary. So in step 1 you can see it is only changing the height, that is upsetting is happening, and in step 2 the front view of the workpiece is being deformed. So this is blocker stage, it is being deformed from the edges, you can see. This is front and the top view of the simulation. It is changing the shape. This is the second stage that is going on. This is step 2. It has come to the almost final shape. Again, I will walk you through the video. The step 1, where upsetting is happening, that is only the diameter is being increased and the length or height is being decreased, and this is how the forces or the strain is happening. Now step 2, the blocker is trying to bring it to a shape. So you can see around the edges the forces are maximum where the contact with the blocker die is there, and in the middle also some changes are happening, and from the edges the forces are transferring inside. These are not forces, it's actually strain how it is going. From the edges it comes inside, and from here itself, as you can see a circle, the strain is extending out. So this was multi-step forming. There are certain applications, for example in wall forging, in hubcap development, in heading process, in ball peen hammer, certain different applications are there. For example in wall forging, I will just play this video very quickly. So there is a simple poppet wall being forged here, in which you can say first this is the billet. First step is you get into this shape, second step is you get into this final shape. You can also fast forward the video just using the YouTube tab here. I am trying to play it in the speed 2 times of the actual speed. You can see the first step is this is being formed, the right hand side is showing, and the left hand side is showing the complete setup. And the second step has now come. There is a blocker step that will turn the top of the valve into the required shape, that is the forged product will then be produced. It is changing the shape. This is application in walls. So let me come to the self-check quiz. The number of steps in which designing of a forming process can be divided. There could be multiple steps, that is shown in this theory are 5 steps. Which of the following product is not manufactured by forming operation? Fasteners can be developed, hand tools can be developed, crankshaft can be developed, lathe bed cannot be developed. Generally in metal forming, the small components are being developed. The large components would need separate presses or so, separate setup workstations. In the multi-step forging, for example, I showed you the example of wall. In the single forging press, using 2 steps, this is being developed. It could be more than 2 steps, 3, 4 steps could also be there. But in a single workstation, using different kinds of the die designs, we can develop. That is how it is developed. So lathe bed is not developed using the forming operation. Which of the following is an advantage of forging? Surface finish is generally not great. Low tool cost, close tolerance, improved physical property. That is one of the advantages. Which of the following may not be the variable that affect the metal forming process? So here amongst the given variables, the surface luster is not significant or not affecting it. In forging operation, fullering is done too. Fullering is a process that is done to upset the materials. The process of removing the burrs or flash from a forged component in a drop forging is called swaging. Which of the following material cannot be forged? Wrought iron can be forged, cast iron cannot be forged, mild steel, high carbon steel can be forged, but the cast iron is the answer. Forging defect due to hindrance to smooth flow of metal in component called lap, it occurred due to So that when I walked through it, it occurred due to the shrinkage allowance that was inadequate. In wall forging simulation of multi-step forging, the number of steps required for wall forging are 2 steps. We just walked through the wall forging simulation process. In the wall forging simulation for multi-step forging, the material of the billet that was there was steel. Let me submit. So I have gotten 10 points from the 10 questions, and these are the again our given answers and the correct answers. I'll come to the home tab once again. 2 more processes I'll walk you through. Very important process here is rolling, because rolling we have studied in extension in the theory classes as well. So this is hot rolling, cold rolling. How is the rolling process going? So there are 2 high mill roll. So we are also the multiple high mill rolls as well. That is 3 high mill, and this is 4 high mill. This is a cluster roll mill. The continuous rolling process, planetary mill is also there. Multiple rolling systems are being shown here, and it's a transverse rolling process that helps to develop the wedges, that helps to develop the components with the varying radiuses as well. This is a transverse rolling process. So shaped rolling sections are also there, in which specific shape could be gotten in one go. For example, railway lines are also produced using the rolling process as well. So let me come to the types of the rolling process. It is showing ring rolling, thread rolling, and wedge rolling. Ring rolling is a specialized type of metal forming operation which reduces the thickness, that is the cross section, and enlarges the diameter of the workpiece by squeezing action as it passes between the 2 rotating rolls. So this is ring rolling process. You can see there is a mandrel, there is a ring, and there is a lower and a upper conical parts here. So this is how the ring rolling process is working that we have seen. Let me come to the next, that is thread rolling. Thread rolling means we try to produce threads over a rod. Then also we can have knurling as well. On the blank, knurling is also done. Certain processes like those are taken here. So there are 4 main types of thread rolling named after the configuration of the dies: flat dies, 2 die cylindrical, 3 die cylindrical, planetary dies. So different kinds of the thread rolling process. You can see upper die and lower die, where this shape or profile is equivalent to the kind of the thread required. The size of the thread, the angle of the thread, everything is provided in the die design itself in this surface. So then 2 die cylindrical thread rolling process, 3 die cylindrical thread rolling process, planetary die thread rolling process. All of these are given here. Let me come to the simulation of the thread rolling. Thread rolling, 3 kinds of simulation are given: by using flat dies, by using 2 set rolls, by using set of 3 rolls. I'll just walk you through the simulation of thread rolling, and I will only try to see the equivalent strain here. So you can see here, if I play the video, so this simulation tells us about the finite element analysis of thread rolling technique using 2 reciprocating well grooved dies here. Well grooved means it is designed or grooved according to the size of the thread that is required. So we note that at a point where the roll first comes in contact, the maximum strain is generated. You can see here the maximum strain is generated at the points where it is coming in contact. So which slowly fades into yellow, that is, then it comes down to green finally, and then into blue color. So the legend is showing the strain that is happening in the initial contact. The strain is high, so then slowly the strain is becoming lesser. So here as high up to 500 megapascal of pressure is used. So this is thread rolling. Quickly you can go through thread rolling, different kinds of the rolling here, thread rolling processes, the different kinds of the simulation setups in different setups of the thread rolling. Other than thread rolling, you can select maybe other rolling processes, and you can keep walking through the different kinds of the setups. So this is how the rolling process is happening here. The force in tons is given, and with respect to time how the force is varying, it is showing in the beginning the force is high, then the force is being reduced. So that is why the strain was also higher in the beginning, that I showed you in the previous video. So I am coming back to the rolling, generic rolling once again. So then I will try to just review my knowledge in the quiz. For example, the first question is alligatoring is a defect that arises in the process of rolling. The smallest roll product that is there is slab. The velocity of ramp used in simulation, the different questions are again given. I can pick some answers here. I am just picking very random answers because the final answers you can see in the final result here. I am just picking some answers and I will click the submit button and you got the answers here. The answers which were not correct are corrected in the third column here, you can see here. You can go through the self-help quiz here. So these are very basic simulations that shows you the varying temperature, varying strain, varying forces which are there. Only I will now come through the one last process, that is sheet metal working. Sheet metal working, as we studied in the theory, there is one sheet in which sharing, forming, finishing, all these processes are taken. So this is, you can say, punching operation is there. So worksheet after punch operation, then blanking is there, we take the blank out of a sheet, perforating, that is punching a number of holes in a sheet, parting the sheet into two or more pieces, notching, lensing, all these processes for the sheet metal are there. This is bending of the sheet as well. Sheet bending machines, set bending setups are there, in which tension is here at the bend area. So bending operations in sheet metal, let me just click U bend punch. So in this bending operation you can see a punch is there, that is coming from the top, and this is a U bend and it is being bent here, and this is how when it just contacted it, I will just replay it. When it just contacted, you can see the forces went very high. And in the end the force would have just one big peak and then come down. So this is sheet metal bending simulation. So here the cross section of the die is rectangular and the bend is produced after this is a U-shaped bend. So this is generic bending. Another bending operation, if I try to pick, I can pick V-shaped bending punch. So here a V-shape bending punch is there with the sheet that is taken as 1 millimeter diameter sheet, and punch velocity is 3 millimeters per second. It is given here, the theory is given here. Maximum punch force is 0.6 ton, that is given here. So this is also bending operation. You can also now go through the self-check quiz in sheet metal as well, and you can try to find the right answers. So this is generic. You can pick any of the operations here in processes, any of the processes, any of the operations in each of the processes. Certain simulations, certain setups, certain cases are given. So this is the virtual laboratory simulation on metal forming. Just a quick demonstration I have given. You can walk through any of the simulations, and that also certain help videos are given by different laboratories across the world. Just walk through them. If any queries, any questions you have specific, you can post them in the forum, and also in the live sessions of this course when we come, you can ask them there. Thank you.